All right, amount of substance. Let's do this. Every equation. So we got N equals CV and N equals M over MR. Okay, these are the two primary mole equations you're going to be using. So let's label all of these and give you any sort of relevant units you need to be aware of. So lowercase n, this is just the symbol for moles, right? C, this is going to be concentration. Concentration. V, it's going to be volume. M is going to be mass. And MR is going to be relative formula mass, RFM. Okay, now what the unit's going to be? Concentration, let's start with this. Mole per decimeter cubed, all right? Really easy stuff here. Volume is going to be in decimeters cubed. Okay, I'll go through some conversion stuff in a minute. Mass, this is going to be in grams. And then moles is just mole, like that. Okay, really easy stuff. Then relative formula mass is exactly the same as relative atomic mass. We're going to be dealing with grams per mole. Okay, grams, the mass per 1 mole of that substance. Okay, now, I'm going to make a little note here. Moles per decimeter cubed and decimeter cubed. When you're given the actual data in the question, because we're dealing with apparatus in the UK that are primarily measured to centimeters cubed, you must convert. All right, so you must convert centimeters cubed into decimeters cubed. How do we do that? Really simple. You just divide by 1,000. Okay, in other words, times 10 to the minus 3. Okay. Right, so those are mole equations out of the way. Really easy stuff. Let's move on to another one, which also involves moles actually, but this is the ideal gas equation. PV equals nRT. Really simple stuff. You only have to pay attention to very specific unit changes here, okay? P is going to be pressure. Pressure, let's spell that right. And that's in pascals, okay? So often you're going to be given this in kilopascals. You're going to have to convert it. V, this is volume. Okay, going back over conversions. I'll go into more detail into conversions in a little bit. I've got some more stuff on that to make it really simple for you guys. But basically, if you're given kilopascals and you need to convert it to pascals, you just times 10 to the 3 or times 1,000. Okay, these are both the same thing, just one is in standard form. Okay, this one is moles. Okay, exactly the same as this. And you can actually feed this into this if you need to. Remember, this is super important. This is for gases. Okay, so you cannot work out the moles of a solid using this equation. It has to be a gas. Okay, this R right here, this is the ideal gas constant, or just gas constant, I should say. As I said, as a constant, 8.31. This value is always going to be given to you, so don't stress about remembering it. T, capital T, is temperature. Okay, and this is in Kelvin. So if you're given something in degrees Celsius, you have to convert it to Kelvin. How do we do that? Plus 273. If you want to go back the other way, minus 273, but you shouldn't need to do this. You want to be converting primarily from degrees Celsius into Kelvin. All right, so that's the first two bunches of equations. Let's move on now. Last point here, I didn't mention actually, super important to remember, the volume is in meters cubed. It's going to be a unique case, but you need to convert from centimeters, if you're given it in centimeters, into meters cubed. Again, you're going to be able to convert it by doing divide by 1,000,000, okay? Divide by 1,000,000, or times 10 to the minus 6. We'll get onto unit conversions later, so don't worry about that right now. All right. Another equation involving moles is going to be N, capital N. This is the way I remember it. You may see it in different ways. Equals N, L. Okay. Now, don't get confused here. I'm going to explain what each of these are. Let's actually change this to be red, so it's sort of clear that it's the actual equation formula that we're dealing with. I do not want you to misinterpret this and get confused, okay? Capital N is number of particles. Okay, that can be ions, it can be isotopes, it can be whatever it is, right? Electrons, it don't really matter. As long as it's a particle, you're all good to go. This right here is moles. Lowercase n, as usual, you shouldn't be comfortable with this. This capital L right here is Avogadro's constant. Okay, 6.022 times 10 to the 23 is going to be given to you, constant. Now, sometimes you're going to see Avogadro's constant written as capital N, A. So if this is what you're given, do not get confused and think that this is this. This is just something I made up to remember the formula for myself. I've never seen it in a textbook or teacher's teacher, but it's just a formula, and I just remembered it that way. If whatever way you want to remember it, go for it, all right? But that's just the easiest way I found to remember it for myself. Okay, so don't get those two mixed up. Really important. All right, empirical formula. This isn't so much as an equation or a formula, but it's just something to remember the method for, okay? What you want to do is you want to look at the moles of the substance you're looking at and divide that by the lowest moles. Okay? In this way, it's going to give you a ratio, and that will give you a ratio for each element. Okay? And then when you get the ratio, for example, like 1 to 2 to 3, that will be able to output whatever your empirical formula is for those respective elements in a compound. Okay? Nice. All right. Let's move on to 3 equations that are very similar. So they're sort of going to feed into one another, right? They're just slightly different. There's a couple caveats between them. So the first one is D equals M over V. You may know what this is already just by looking at it, okay? I'm going to do it in red again. I'm going to try to stay consistent with these colors. D equals M over V. What is D here? This is density. Density, okay? M, guess what M is? Mass. Pretty easy here. V, volume. Okay, not velocity, volume. Okay, so this is density equals mass over volume. Really simple equation here. Now I'm going to go over some units. Density is going to primarily be in grams per centimeter cubed. Okay, kind of a weird one. Mass is just going to be in grams because you've got to keep the mass units the same. Volume is going to be centimeters cubed. Ooh, so you can see how this changes up. Normally, you're given a volume and you have to convert it into decimeters cubed so that the volume units remain consistent. But here, the density is actually in grams per centimeter cubed anyway. So just be really careful in the question that this is the standard. But if for whatever reason they ask you to calculate the density in grams per decimeter cubed, you will have to convert the volume into decimeter cubed. I hope that makes sense. Okay, now, very, very similar to density is mass concentration. Okay, mass concentration is mass over volume. Okay, so how does this differ from density? It's honestly basically the same thing, except the units. Okay, so this again, MC is mass concentration, and this is going to be in grams per decimeter cubed. So this is what is referred to as mass concentration, but if for whatever reason in the exam question they ask you to calculate density to this unit, then it is essentially the same as mass concentration. But by default, density is going to be in grams per centimeter cubed. Really important to remember that. M is mass again, this is grams. V is volume again, but this is going to be in decimeters cubed this time. Okay, hopefully that makes sense. And then we're going to feed this into a very similar equation. S equals M over volume. Okay, now the volume is going to be actually a fixed unit here, 100 centimeters cubed. Okay, so what is S? This is referred to as solubility. So in an amount of substance calculation, you may need to calculate the solubility of a compound, for example, like a group 2 hydroxide or something like that. M is going to be mass again, and this is going to be in grams. And then the volume is this, but it's fixed, okay? Now, the standard unit of volume for solubility is 100 centimeters cubed, but this may change. So just keep your eye on the specific question and see what's going on. So this is volume, okay? As you can see, everything falls back to density equals mass over volume. So all of these are mass over volume in each case. It's just slightly different caveats depending on the type of equation you need to use for the very specific question you're given. Right, good old PV equals nRT. This is going to be regarding changing conditions, okay? So this is our standard PV equals nRT equation. Let's rearrange this quickly and look at how you can use it when conditions are being changed and some are remaining constant. So if we take everything to this side to make it PV divided by this, divided by nRT, this we can think of as our joint or combined gas expression, okay? And this is going to equal the final gas expression once conditions have been changed. Okay, you may be super confused what I'm talking about here, but hopefully it will make sense in a second, okay? So what I'm going to do is I'm going to write what this would become in an equation, and it's really useful to remember this equation, okay? So R, what is this guy right here? R is a constant, gas constant, 8.31, right? If you change conditions of a gas, you can change any of these four variables, N and T, PV and T, okay? R is always going to remain constant when you go from one condition to the next because it's a constant, right? So what we can make this equation become is PV over NT equals PV over NT. And what is going on here? Like, what does this mean? How does this help us? You can think of it as P1V1 over N1T1 equals P2V2 over N2T2. So this is going to be the equation that you kind of remember off by heart if you can when conditions are being changed. And what you want to do is you just want to cancel and entirely remove from this expression anything that does remain constant, just like we did with the R right here. Okay, there's a few different laws that are associated with gases that you do not need to know for A-level. I'm just going to exemplify how this can be converted into these four through keeping certain things constant. So let's say we want to keep moles constant, Rn, right? That's going to be P1V1 over T1 equals P2V2 over T2. Okay, so you can see how you just cancel the mole and get rid of it, right? Pretty simple stuff. Now, let's say we had N and T are constant. It's just going to be P1V1 equals P2V2. You're going to see how this flows, right? P and N are constant now. V1 over T1 equals V2 over T2. Okay. Last one, Avogadro's law. V1 over N1 equals V2 over N2. You see how easy this is, right? I would not suggest remembering all these four laws, all these four equations. It's just extra info that's going to like soak up stuff in your brain. You want to remember just one and then remember the fact that you cancel anything that's constant. Okay, and keep the rest present. So like, great, like I know these equations, how does it help me? All you got to do is rearrange, okay? Throughout calculations in chemistry, just get really solid with rearranging. So let's say you carried out the Boyle's law right here. The moles and the temperature are constant. We want to find what the final pressure is, i.e. pressure 2, right? So then you would rearrange that to be P2 equals P1 V1 over V2. And then you'd carry that out in exactly the same way as whichever variable you're looking for. Just make that the subject and rearrange this equation as needed, okay? Pretty simple stuff. Very similar to this right here, dilutions. Okay, so let's say you have a beaker of solution. You want to dilute that shizzle, add some distilled or deionized water. So we're going to have C1V1 equals C2V2. Okay, very similar to how you equate the gas laws here and remove anything that's constant. Now, there's not going to be a constant when you're diluting. There is for moles, okay? The moles is going to remain the same. So that's why if you think about the mole expression, N equals CV, the moles is essentially removed, and this CV equals CV, okay? Kind of confusing, but hopefully that makes sense. Now, all you have to remember is rearrange as needed, okay? Super simple, just like PV equals nRT, keeping things the same. If we wanted to find the final concentration after things have diluted, we would just keep this as the subject. So it would be C2 equals C1 V1 over V2. See how easy that is? And you can just use that as you need to, okay? All right, molar gas volume. This is essentially just like a law that you can remember, like a caveat, okay? 1 mole of any gas has to be a gas. You can't be doing this with liquids or anything like that. 1 mole of a gas, as long as it's at room temperature, 25 degrees Celsius or 298 Kelvin, if you're given the temperature value in Kelvin, and pressure at 100 kilopascals. Now, you're also going to be given this in atmospheres. So 1 atmosphere, this is exactly the same as this. For chemistry, it's not really, it's 101 kilopascals, but for chemistry, they put it to 100 kilopascals. So we're going to be doing this atmospheres, okay? This is going to equal us very specific volume for that gas to take up, and that is 24 decimeters cubed. Okay, and you can use this in certain questions. They're going to be minor questions here and there that pop up, But if they tell you that the temperature and pressure is kept constant and they are at room temperature and pressure, you can know that 1 mole of said gas is going to occupy this amount of volume, this volume of space. Okay, hopefully that helped you. Let's move on. All right, next up, we're going to go through the simplest way I could possibly imagine explaining unit conversion to my students. All right, smaller. Let's say we have a smaller unit and we want to convert that into a bigger unit. Okay, we are going to divide. If we want to go the other way and go from bigger to smaller, you're going to multiply. Okay, so let's use a very specific example that you can sort of picture, okay? Centimeters going to decimeters, then going to meters. As we go from centimeters to decimeters to meters, is this going from a smaller unit to a bigger one or from a bigger one to a smaller one? That's all you need to think right now. Hopefully you know that centimeters is a smaller unit of measurement than decimeters, okay? So if we're going from smaller to bigger, we simply want to divide, okay? And if we need to go the other way for whatever reason, you multiply, okay? And you would multiply and divide by a factor of 10, okay? So divide by 10 times by 10, okay? Similarly, when we go from decimeters to meters, you're going to divide by 10 again because we're going from a smaller unit to a bigger unit. So you divide, the difference is 10. So we're going to do divide by 10. And if we're going the other way, times by 10, okay? So if you go from centimeters to meters, you're going to divide these by the factors multiplied, okay? So if you go all the way from here to here, you divide by 100, okay? And if you go all the way from here to here, you times by 100, okay? That is the simplest way I can think to explain it. Now, this is really important to remember. If there is a power, so for example, like we're going to use the example in a second of centimeters cubed, you apply that power to the difference. Okay, so I'll explain what I mean. Let's get my thing on the page again. Centimeters to decimeters to meters. This is going to be cubed, this is going to be cubed, and this is going to be cubed because we're dealing with volumes primarily for this sort of unit, right? Now, what you want to do is you want to divide it by 10, just like we did up here, okay? Divide it by 10, just like we did here. And if we go in the other way, times by 10, other way, times by 10, okay? How has this changed? You just apply the power of the unit, so centimeters cubed, to the difference. So you do divide by 10 cubed, divided by 10 cubed, times 10 cubed, times 10 cubed, okay? What is 10 cubed? 1,000. Okay, so you can see how this directly lines up with how you're taught to do the conversions for your volume units in chem, all right? And again, if we want to go all the way here from here to here, you divide by 100 and then apply the power. 100 cubed is 1 million. But you're going to see it often written as times 10 to the 6. Sorry, divide by 10 to the 6. In other words, divide by a million. Okay, just because they like everything to be in tens for standard form. Okay, so hopefully that's units, guys. Hopefully that helped you. Not too complicated, to be honest, if you just practice it a little bit. And remember these rules. Smaller to bigger, you divide. Bigger to smaller, you times. If there's a power, you apply that power to the difference. Okay, pretty simple. All right, percentages. Okay, so you're going to have 3 equations here that deal with percentages. The third one is primarily, well, not primarily, it's always to do with practicals, right? So let's go through the first one, percentage yield. So how would you do this? This is going to be actual yield or actual mass. Remember, yield is just mass, okay? Over theoretical yield. And then because it's a percentage, you've got to chuck on that multiplied by 100 at the end, okay? What is this theoretical yield? How are we supposed to know what this is? This is just your calculated mass. Okay, so whatever mass you carried out in a calculation prior to this, sometimes they will tell you in the actual question wording, but it's going to be a theoretical yield. This actual yield is like what would have happened if you did the experiment. Okay, because theoretical yield is going to be higher than the actual yield just because in real life, the actual yield doesn't have perfect conditions to carry out the experiment or carry out the industrial process or whatever you're dealing with, right? So that's the first percentage equation. Next one is percentage atom economy. Okay, now Let's rewrite that economy because that was a bit dodgy. Okay, economy. This equals mass of desired product. Now, when I say desired product, all this is going to be is the mass of the substance they ask you for. So if they said calculate the percentage atom economy of carbon monoxide or whatever it may be, you would carry out that calculation and your desired product is carbon monoxide. Okay, hopefully that makes sense. And this is going to be divided by the mass, more specifically the total or sum of the mass of all reactants. Okay, so we put this mass of reactants in. We got this mass of our desired product out. This is our atom economy. Okay. Last thing, because it's a percentage, times by 100. All right. Now, really important thing to note here. The mass of the desired products and the mass of reactants, let's write this out very clearly, must use the mole ratios to calculate these. Okay, so normally you don't have to do this when you're dealing with masses, but for this, you have to think of n equals m over mr, and then you're going to incorporate that to be m equals n times mr. So for the purposes of this, the moles is going to be the mole ratios given to you in an equation. Okay, so let's do a little example here. Let's say an equation dealt with 2H2O. This is not specifically the moles of the water within the calculation that you carried out, but it's going to be the moles of the water that reacted in a fixed ratio, or the moles of water that is produced in a fixed ratio. So the mass of that then is going to be 2, because that's our mole ratio, multiplied by the mr. If we have 2 lots of hydrogen, that's 2. Then oxygen is 16, so that's 18. And this is going to give you 36. Okay, that would be our mass that we input into here. And you're going to want to do that not just for the desired product, you need to do that for everything involved. Really important to remember that for percentage atom economy. Last percentage to do with practicals. Let's change to red so we make it nice and clear what's going on. Percentage uncertainty. Percentage uncertainty equals, this is going to be plus or minus uncertainty. Now the uncertainty is going to be given to you, so don't freak out about that. It's going to be, for example, like 0.05. That is going to be given to you. Okay, and this is going to be divided by the measurement taken. Really common example is going to be like mean theta, okay, when you're carrying out your titrations. And again, because it's a percentage, you times it by 100, all right? Now, this is also super important to remember. The uncertainty must be the total, okay? So let's just say you took out one measurement reading, and that was 0.05. And then you took out a second measurement reading, and that was also 0.05, right? The total uncertainty would be 0.01. So that is the value that you would have to put as the numerator in your equation, okay? Now this plus and minus, you can essentially ignore this. It just means that whatever value you have, let's say we recorded a value of 0.3, the plus or minus uncertainty just means that the actual value that you could have gotten is within a range. So if it's plus 0.05 uncertainty, it can be between 0.035. And if it's minus 0.05, it will be 0.25. So in reality, the measurement can be anywhere between here and here, according to the uncertainty, okay? But we may have got a reading of 0.3. This just accounts for the range in the measurement. If you want to grab yourself a free PDF formula book, check out the link down below, and you're going to be able to grab all my free resources as well. If you're struggling with chem and you need that little bit of extra help to boost your grade as quickly as possible, check out my tuition offers. But regardless, this video should help you and put you in a good place to solve all the calculations you need to.